The hanging mass problem involves a mass hanging from the bottom of a string. We can call this mass m. The problem is to determine the acceleration of this block. The way we can do that is from using Newton's second law, which says that the sum of the forces, or the net force acting on the block, will be the mass of the block times the acceleration of the block. So as you can see here, trying to determine the acceleration means we must know the net force. So the way that we're going to find the acceleration of the block is by first finding the net force acting on the block, which means we need to figure out what forces are acting on this block. So the first force that acts on the block is actually the weight, which is gravity, the force of the earth pulling the block downward. The second force acting on this block is this rope pulling the block up. We can call that T for tension. Now in this situation, what has happened here is, as you've seen, I've drawn the tension much smaller than the weight. So if the tension is less than the weight, what ends up happening is we'll have a negative acceleration, or a downward acceleration. So the acceleration is no longer unknown. We know that the acceleration is going to be in the negative direction. And the reason is because the weight exceeds the upward tension, which means the acceleration will be in the downward direction. Another possibility is that the tension is equal to the weight. Now the weight is always going to be a fixed magnitude, because if we have the same mass, the same earth, the mass and the earth will always attract each other equally. But what if this rope were pulled harder upward? In fact, what if it were pulled so much harder that it was actually equal to the same strength as the weight? If the tension in the rope were equal to the weight, what acceleration would result? In this case, there would be no acceleration. The acceleration would be equal to zero. The two forces would balance out. There would be no net force. And if the net force is zero, the acceleration has to be zero. The third possibility is that the tension was greater than the weight. So suppose this string were pulled or yanked really hard upward, so hard that it exceeded the weight. Then what would happen is the acceleration would point in the upward direction. The tension would exceed the weight, and our block would change its velocity upward. So if the tension is greater than the weight, we'll end up with an upward acceleration. Or we could call this a positive acceleration. We should be able to use Newton's second law to figure out a mathematical expression which will yield any of these three results. We'll do this by first drawing the picture again, starting over from the beginning using Newton's second law. So we've got our mass hanging from the string, mass m, and Newton's second law, which says that the net force acting on the block is equal to the mass of the block times the acceleration of the block. Identifying the net force requires us to remember that there is the mg force acting downward, the weight, and the tension acting upward. Remember that the acceleration was unknown. We didn't know which way the block was going to accelerate. And lastly, just to be very clear, we'll want to create a coordinate system to define what direction is positive. Let's just use the default coordinate system where up is positive, to the right is positive. This will just help us add the vectors together. So here, when we want to find the net force, we'll say that the tension is pointing in the positive direction, so we have positive tension, plus this weight, mg, which is pointing in the negative direction, so it'll be minus mg, and that's going to be equal to ma. We're trying to find the acceleration, so all we have to do is just solve this expression for a. We'll do that by dividing both sides by m. That'll give us a equals the quantity t minus mg all over m. We can simplify this a little bit more by taking this m and dividing into both these terms here. So give us a equals t over m minus mg over m. In this case, the masses here will cancel out, and we'll just have the acceleration of the block is T over M minus G. Now this expression should contain within it all three of those possibilities. So what we want to do now is to just check to make sure that this expression is true. Does this work? Is this correct? The first way we'll check it is by checking to see, remember we said if the tension was less than the weight, we said that there should be a negative acceleration. So we're going to try to see if that's true. So let's take tension is half the weight. Half the weight is less than the weight. So let's see what happens if we plug in for the tension in this expression. If we plug in for tension, half mg divided by m minus g. Let's see if we get the predicted negative acceleration. So here you can see that the masses will cancel out, leaving us with the acceleration being half g minus g. So this is half of g minus 1 of g. And 1/2 minus 1 is equal to negative 1/2. And there's our negative acceleration. As predicted, we've got a negative acceleration. The second scenario we looked at was when the tension was equal to the weight. In this case, the sum of the forces is going to be 0, so no acceleration should occur. Let's see if our mathematical expression bears that out. If we plug in the tension being mg divided by m minus g. Here the masses will again cancel, leaving us with a equals to g minus g. Well, g minus g, that's 0. So we get exactly what we predicted, that there would be no acceleration. This is also called equilibrium, where you have a balance of forces, no acceleration occurs. The third situation was the tension is greater than the weight. To check this, we can say the tension is double the weight. Let's go ahead and plug this in. A equals to double mg divided by m minus g. Once again, the masses cancel. We have acceleration is 2g minus g. So this is 2 of something minus 1 of something, and 2 minus 1 is just 1. Let's get the acceleration is equal to g, which is a positive acceleration, just like we predicted before. So here we see our predictions of tension less than mg, tension equal to mg, and tension greater than mg. They give us exactly what we predicted before we even did any of the math, which indicates to us that this expression for the acceleration is correct. We used Newton's second law, we drew a little diagram, determined the net force, solved for the acceleration, and this mathematical expression contains all three possibilities for the acceleration of the block hanging from the string.